Okay, so today's positive theory of equilibrium. So what we want to do is basically try to understand additional properties of general equilibrium, namely existence, and why we care about existence. So we know that general equilibrium is mathematically a system, a nonlinear system of equations, right? So if you do this, right, then we want to know whether, in fact, this system is coherent. So internal consistency, right, which amounts to existence. And after finishing with existence, we want to also establish uniqueness. So why do we like uniqueness? Because it's about making predictions, right? So say you are basically hired in the Fed, right, in the Bank of Canada, or by a consultancy firm. Then so you're asked to model an economy. So you come and model supply and demand. So you have a system of equations, many markets, heterogeneous consumers, many households. So you're able to write down the econ model. So what's the first thing you should do once you have written down general equilibrium model? So you have to show, to demonstrate, or use some theorem, right, from this class, where under some assumptions, then you are assured that the system of equations that you have written has the solution, right? So this is the most basic question of any general equilibrium model. So the question about existence, okay? So to start with, does every general equilibrium setup has an equilibrium? Sorry, does any competitive market setup has an equilibrium? And the quick answer is no, right? So general equilibrium can fail to have general setups of markets can fail to have generically an equilibrium, right? So there are many situations in which there is no equilibrium whatsoever, okay? Now we want therefore to find sufficient conditions on behavior, namely preferences and technology, that will ensure that I will always have existence, okay? So that's our first task. So everyone understands why we want that. So basically we want to ensure internal consistency of our model, okay? Any questions? Okay, so then we go to back to this definition of the well-rational equilibrium. So given a private ownership economy, when we have primitives, preferences, production sets, all of them heterogeneous, endowments, and then the shares over firms, right? So ownership structure. We have an allocation, which is a matrix, and a price vector P, and they constitute a well-rational equilibrium if the following happens. One, firms profit maximize. So this is just the statement of profit maximization. So the Y star is profit maximizing for all production sets. Two, consumers' utility or preferences maximize, subject to the endogenous budget constraint. Here, as you can see, we have endowments and the profit share, okay? And finally, markets clear. Okay, so this is aggregate supply is equal to aggregate demand, and then we have a shift by the endowments. Okay, so this is known. We are going to study now this simple case of pure exchange. Okay, so the production set is going to be simplified to the Edgeworth box setup. So this means that there is only this free disposal technology. Free disposal technology means I can just throw to the trash can any excess thing that you don't like, okay? The consumption space is the positive order. So here, people just can have positive quantities of goods for simplification. All of these assumptions are important for existence, right? Even if you can write models more general than this, then our theorem won't apply, right? So remember that. So, of course, this theorem will be easy to extend to production setups, but right now we want to prove it in the simplest case, and even the simplest case is hard to prove. So, okay, so now we want to simplify this definition with a pure exchange. Profit maximization simplifies to this. So basically, it says that achieved profits with a free disposal technology are equal to 0. And then in free disposal technology, the output, the production, the supply is just less than equal than 0, because you can actually dispose of things, right? But you don't produce anything because pure exchange. And this happens for positive prices. So there may be things that are not worth anything in this economy. So the price will be 0. And for those, right, essentially you're gonna throw away things in the trash can, right? So things that are worthless, you're gonna throw it in the trash can. And then for consumer utility maximization, we're gonna simplify notation by basically assuming that the outcome of preference maximization is a well-rationed demand function. So we're assuming there is such a function, namely the product of maximizing a preference over this endogenous budget, which is by chapter 3, Mascoli, Wilson, Green, a function of prices and a function of endogenous income, right? Because profits are 0, then all this term that was complex here, which basically is the summation over this, profits become 0, right? So you don't care about that. So the only thing that you have here is prices times endowments, okay? So remember, this is a function, so it already has the preferences there. So this is already the product of preference maximization, okay? So this is already a preference maximizing demand function. And then market clearance, right? So that means that if you take the aggregate demand minus the aggregate endowment is equal to the net supply. And what is the net supply? Basically is 0 when things are desirable and something negative when things are going to the trash can, right? So if there is excess endowment and you don't want it, then this is going to the trash can, okay? So that's what's happening. So everyone gets it. So very simple. So now, let's simplify even more. So in a pure exchange economy in which consumers' preferences are continuous, so now we're assuming more stuff. These additional assumptions are taking us closer to showing existence, right? So again, these are sufficient conditions for existence. They are not necessary. So you can still have existence without them, right? But you are not sure anymore, okay? If you have these conditions, you're going to be sure. So in pure exchange economy, in which consumers' preferences are continuous, strictly convex, importantly, and locally non-associated, prices are weakly greater than 0. And our rational equilibrium price vector is basically any price that solves this inequality, okay? So what is this inequality? Well, as you can see, it's basically a combination of all these 3 conditions before. So we're going to show it, right? That's the case. So take the weekly positive price, and then this is a well-rational equilibrium if 1, 2, 3 hold from the definition before. So this basically combining them will give you this inequality. Why? Because what you're doing is replacing the demand from 2 into the market clearance condition, and then you're replacing the condition 1 here, right, such that you get less than equal than 0. So putting all these 3 things together, you get basically that this term here, which is the first part of the summation, this is a summation over I of the demand vectors, right? So for a given price and the fixed endowment, you get the demand of this good. If you add up over individuals, you get the aggregate demand. So this is aggregate demand, and then you subtract from this aggregate endowment, right? Which will give you the aggregate excess demand, okay? So this object is called aggregate excess demand. So an equilibrium is a price that makes aggregate excess demand less than equal than 0, right? So of course, there are things that you don't want or anyone wants, and therefore the negative numbers. And when things are desirable, then you're gonna get this strictly this equal to 0, right? Okay, so remember here, crucially, we have only local non-association, right? We don't have monotonicity. So now, the important thing here is this statement, if and only if. So if I have this condition being satisfied, which is just aggregate excess demand. So how many, by the way, what is the dimension of this equation? So each x sub I is an L-dimensional vector, a column vector of size L, right? So this thing here gives you L inequalities, okay? It's a vector notation. So you have L equations, okay? So namely and generically, the pure exchange general equilibrium setup is basically a system of equations with L equations, okay? One equation per good, excess demand per good, okay? So we have L equations. And how many unknowns? The price. The price is the only unknown at this stage. And the price basically is size L again, okay? So it's L equations with L unknowns, okay? So, and here, what we're showing basically is that this simple statement with L equation is equivalent to the definition of this definition 81, okay? So the other way, so imagine this system of inequalities with L equations hold. Then we let the yi star to be equal to the excess demand, okay? So now this thing here is going to be the supply. Now we check that if I multiply this excess demand times prices by local non-satiation, I know this is equal to 0, right? Because you have to be at the budget line. Okay, so multiplying P times omega gives you the income, and then P times X has to be at the income because this is locally non-satiated. We already proved this. And then basically we let X star be equal to the demand. So 1 and 3 hold. So what I'm saying is that just checking these L equations is going to guarantee that you are preference maximizing, you live at the budget, the market's clear, and then also profits are maximized at 0 in the pure exchange equilibrium, okay? So we know that the difference vector is the consumer's I net or excess demand for each good according to which he had in terms of endowments of a given good, okay? So one important caveat in all this Mas-Colel chapter is that this excess demand is a function of both of prices, right, the unknown, but also of the following parameters. So of endowments, right, which is the primitive, the thing that is changing in the market potentially, and of course of preferences. So preferences here are captured by the demand, so the function x, right? And endowments are inside the function x as an argument. So this equilibrium is determined by the primitives, right? But the only variable here is prices. So in the Mas-Colel notation, he's only writing this function as a function of the variable, right? Which is price. Fixing endowments fundamentally. So fixing endowments turns out to be a very important thing for Mas-Colel, and this is going to drive a lot of the results we will have later on in this chapter, okay? So have it in mind. So definition 82, let's define now excess demand for each individual. So I'm going to use a new symbol, Z sub I, and this is just the difference of the vector size L of demand functions evaluated at price P and endowment omega I minus omega I. So this is the individual excess demand. Okay, so just a definition. And now the aggregate excess demand then is the summation over individuals of the individual excess demands. Okay. And again, using the Einstein notation, look that the symbol here now omits the sub I. Okay. So now there is no longer sub I, which is a summation over I. Again, what is the dimension of this object? This maps prices. Remember, endowments are fixed, right? But once you fix them, so basically you're mapping prices, which are size L, positive, to something in RL, because the excess demand can be negative, right? And it can be 0, can be positive. So this is RL. So everyone understands? So this is the key object here in this chapter. So our primitive in this chapter is basically the aggregate excess demand. Okay?
Sorry, I have a question.
Sure.
Why we have the price will be non-negative? I mean, in this setup, is that because we have a free disposal technology?
Can you repeat again? So I didn't understand the
I mean, here we have the price cannot be negative. I don't know why this came from.
Oh, yeah. So in particular here, we are assuming that prices, so if you see from the definition, right? So it says P is weakly greater than 0, this is part of the definition, right? So if you have negative prices, then you can have positive profits, and then you will be able to write this down as you have actually to share these profits, okay? But in particular, this will be breaking the free disposal, right? There,
Yeah.
if you have negative prices, then you will have profits. Okay.
Yeah.
Okay. So actually,
I-
that's an important question for the core exam. So a classical question in the core exam, again, three questions that I don't like, but they are there historically, right? And not only for Western, for every place that you go to study this, is let's remove the predisposal assumption, right? So have that in your mind as we go through, but one of the key insights is that if you have negative, so having negative prices in this pure exchange setup means basically that you lose predisposal, okay?
Yes, but I mean, I was thinking we can also um, we can also give some restrictions on the preference to have the price be non-negative, but not
Yeah,
on the supply side.
yeah, that's true. Monotonicity usually does that. That's true.
Uh,
But in this case, right, so we were assuming prices are positive. So I'm just following here uh, this definition. So they don't have to be. Again, so so just to clarify, right now we're studying everything with non-negative prices, but you can actually define things with negative prices, right? And they will mean to be subsidies, right? And
okay,
so yeah, this thing is always more general, but we're looking for a canonical example where things actually have existence, okay?
okay, thank you.
And then the key that I want you to highlight is this aggregate excess demand, right? So why this is important? Because basically this is a shortcut notation for something that potentially is very complex, which is a size L nonlinear system of equations, okay? So you have an unknown, the price, which is size L, and you have L, a system of equations, okay? So you know that general equilibrium, right, was invented by several researchers across Europe, including Leon Walras in France, right? So he has a famous blunder. So Leon Walras basically saw this, right? Was able to write down this system of equations, and he was an engineer, right? He was a trains engineer in France, of course, better in math than most economists at the time. And then basically he said, look, and given that we have general equilibrium defined as a system of equations with L equations and L unknowns, we are sure that there is a solution. Okay, so that claim obviously is wrong. So who among you can tell me why this is wrong? So even simplified, think that the system of equation is linear, right? So connected with linear algebra. So you have a system of equations of size L, right? L equations and L unknowns. So is that enough, as Walras thought, for existence to be guaranteed?
No.
Yeah.
If there's, what would it be, less equations than unknowns, then you can't solve for the unique solution. Or if there was more, then there could be infinite solutions.
Yeah. So namely, a system, a linear system of equations, right, can have three outcomes. So it can have no solution, right? It can have a unique solution. It can have multiple solutions, right? And so it all depends on the rank, at least for the linear system, right? So if you have full rank, the rank of this matrix in the linear system of equations is equal to the unknowns, then you have an invertible system, and then you have a unique solution, right? In general, having less than full rank, you can still have solutions, right? But lack of a solution is a bigger issue because it means basically that your system of equations is contradictory, right? So it's not internally consistent, okay? So it leads to a contradiction. So the same can happen for a nonlinear system of equations, okay? So Walras obviously was wrong, right? And this is a famous mistake people still remember until this day, right? So even in this class, I'm still remember Walras blunder. So don't do that. Okay, so now what we want to show is basically sufficient conditions that will ensure that I have a solution. And of course, given that the system is nonlinear, I cannot do a simple argument such as the rank of the matrix, right? So I have to do something else. So now, so I think, so if you can check quickly in Google, when was Leon Walras writing about general equilibrium? I think it was about 30s. I forgot completely about the time. But so Leon Walras, Wilfredo Pareto, and others, wrote the general equilibrium theory very early, right? Before the before World War II. But actually, it took a lot, actually, around the 60s to be able to prove existence, okay? So in all that time, economists used general equilibrium arguments, and we had general equilibrium as a model, but we didn't know whether it was coherent generically, okay? So a lack of existence of general equilibrium was an open question, and it was for a while, okay? And so now the story of the existence of general equilibrium, how people came to prove it, actually is a very exciting story. So I will tell you a little bit about today. So someone wrote in the chat. Yeah, so actually, great. So it's earlier than I remember. So it's in the 19th century. So Leon Walras was writing this in the, according to Schumann, by 1889. Okay, so this was very early. And then since then, economists didn't know if general equilibrium had a solution in general. Okay? So this was a big issue, the issue of existence of general equilibrium. Okay, and why do we care that there exists a solution? Because else we cannot ensure that this theory is coherent. We understand. So if generically, right, we only have very special cases under which this exists, then we know our theory is not great. But if generically for a set of sensible assumptions on behavior, we ensure existence, then this is amazing, right? Then our system at least is coherent. Okay. So the first problem and classic problem is existence. So now this was open since the 19th century, and it was solved around the 60s, I think. So you can check the Arrow-Debreu proof, Mackenzie proof of existence of general equilibrium in Wikipedia. And this was this actually is Nobel Prize worthy, right? We have the fake Nobel Prize in econ, but it's cool. So, and then this was given to Arrow and Debreu. However, I also told you about another name, Mackenzie, right? Professor of Rochester. So he actually did the proof first. But Arrow and Debreu, they powerful people, and especially Debreu. It's kind of a novel, so you can read it all online, the history about general equilibrium. So they actually blocked Mackenzie, especially Debreu, that was an editor in Econometrica, and basically was sitting on this paper forever until Arrow and Debreu were able to prove their result. Okay, so actually the result by Mackenzie is correct, and it was first. And a lot of people actually refer to this proof as the Mackenzie Arrow Debreu. But Arrow Debreu, they won the Nobel, and in the end, they won the history, right? So I'm telling you, don't forget about Mackenzie, right? So he was the guy not in the top 10 in Rochester, actually very close, and he did it first. Okay, so Mackenzie did it first, and basically what they show is this big prize, which was existence of general equilibrium. Okay, now surprisingly, they actually were not original, neither Mackenzie nor Arrow Debreu. All of them copy our friend John Nash, right? And the mathematicians. So John Nash is more famous, right? So I'm sure among of you, many of you have seen A Beautiful Mind, right? Movie. And and basically he had many contributions, not only the existence of a Nash equilibrium, but his shining contribution, at least the one that earned him a Nobel Prize, was that he was able to prove that a generic game, right, has a solution in mixed strategies. So there is a generic solution for this notion of equilibrium that Nash created that extend, the zero-sum game, like von Neumann Morgenstern, right? Sorry. So these contributions, in game theory, even if game theory was younger than general equilibrium, the existence of the Nash equilibrium was proven first. Okay. So the key innovation was that Nash, being a mathematician, he basically had access to the knowledge about fixed points. Okay. So fixed point theorems that you will learn with Maria. So Maria is teaching you the math class, right? So at some point, you're going to learn about fixed points more clearly, right? Today, we're going to see an application of fixed points. And the idea of fixed point is very simple. It's basically that you have sort of mappings of functions that map a vector to itself, right? And basically, if a function has this property, you can use it to show existence of system of equations. So the trick is basically write down, modify your system of equations in a way that it becomes a self map, or basically a map that maps prices to prices. And once you have done it, there are some properties of these functions, such as continuity and others, that will allow you to conclude that there is a fixed point. And the fixed point basically means that if I evaluate this map in a vector, for instance, the price, then it will give me back the same price, okay? And that's why it's a fixed point. And if you do that, then you can connect this to the original system of equation and say, look, this fixed point is actually a solution to the problem, okay? So in the theory of game theory, you will learn it again, and basically there is a fixed point there with best responses, right? But here is all about the price. So the price is going to create a fixed point, okay? So it's not as transparent as in general equilibrium, as in game theory. Here is way more complex. So the real innovation of Aaron DeVries and Mackenzie was to be able to write down, rewrite the general equilibrium setup in a fixed point setup. So a lot of what we're going to do next is going to be this very heavy math in order to write down our general equilibrium setup as a fixed point problem, okay? So don't be scared. It's just a lot of math hard work. And I want you to tell you this because you have to really understand why we're doing this. And why do you care if you want to become an apply guy, right? So why do I want to prove what Aaron DeVries did? So they just did it, right? So the reality is that in many cases, right, as I told you, many of you will become structural guys. So that means you will write down some model, some system of equations. And then, you know, part of your work as a modeler will be to be able to check whether your model has a solution, right? So the classical way to check this is basically by doing what I'm going to describe. So you can see this as a proof of concept of what you can do. So basically that means that if you are able to write down your particular model as a fixed point problem, right, then you can apply the theorems by the mathematicians for fixed points, right? So that's what basically econ theories do. So we don't invent new math, right? So most of econ theories don't invent new math. The real work that we do is their work, right? It's basically rewrite the economic model in a way that I can apply a new result or a useful result from math, right? And what we're going to do today is exactly that. So we're going to rewrite this as the object of math, and then checking assumptions of the mathematical theorem that I want to use. In this case, is the Kakutani's fixed point theorem, right? So I'm going to verify the conditions under which the Kakutani fixed point theorem is valid, okay? So Aaron DeVries never proved a fixed point theorem. They are just being users of the mathematical innovation, right? Such as Nash, he didn't invent the fixed point theorems, right? He just used them, okay? So Nash, in that way, he was actually became like an economist, and that is why he didn't earn I think it's the Abels, I forget the name of the math prize. He didn't earn it for the game theory contributions, right? He earned it for other contributions in partial differential equations, because what he's doing in the Nash contribution, in the Nash equilibrium contribution, is only applying a fixed point term, right? His contribution is more about modeling, okay? So this is what we're doing to is modeling. This is the very work of modeling. So rewrite your very general model in a way that I can apply a theorem, and this theorem is the Kakutani's fixed point theorem, okay? So in particular, right, I'm gonna find out this corollary is gonna be useful in a second. So a P, a vector in RL, is an equilibrium price vector if and only if I put it inside the excess demand, it gives me less than or equal than 0. What are the dimensions of these objects? This 0 is a column vector of size L, okay? Again, Mas-Collet notation is not the best, but this 0 is a vector 0, okay? Moreover, if the set of any good L evaluated at P is equal to 0, that happens when prices are positive, right? And basically, if prices are 0, then this thing you don't want it, therefore the excess demand is negative, okay? Got it? So now, let's specialize even more the assumptions. So the consumer's preferences are strongly monotone. So now this is more than locally non-associated, right? on top of being continuous and strictly convex, the price vector is strictly positive. So some among you ask, what conditions can I impose on preferences to have positive prices? Well, prices will be strictly positive whenever preferences are strongly monetary, okay? So stronger than locally non-associated, okay? So then you have positive prices. And then basically the excess demand, an equilibrium is a price such that makes excess demand exactly equal to 0. So from now on, we're going to study this problem, which is simpler, right? Because we don't have to deal with inequalities. This is just a system of equations. It's not a system of inequalities, right? System of equations because there is a 0 there. Okay, and now, right? Basically, I want to show some properties of this excess demand. So these are actually is a long result, but it is actually very simple. So let me make it a little bit smaller. So suppose that for all individuals I, you have preferences that are continuous, strictly convex, and strongly monotone, right? Suppose also that you have that endowments are strictly positive in the aggregate, then aggregate excess demand defined for all prices satisfy the following properties. First of all, the excess demand is continuous. Easy, right? Summation of continuous demand functions, because we know that if you maximize from chapter 3, we know that demand functions are continuous, right? So we have that this summation over excess demand functions, individual excess demand functions which are continuous mappings, is itself continuous because continuity is preserved under summation. Okay, so one is easy. Second, if you have a summation over functions that are homogeneous of degree 0 on prices. So first of all, why the excess demand is homogeneous of degree 0 on prices? So remember that if I scale up prices by alpha, prices enters in 2 places. They enter in the first argument and in the second argument. The second argument is multiplied by the omega, right? The endowment. But basically what we're doing by increasing alpha here is you're increasing the income by alpha and the price by alpha, right? So we know by chapter 3 that in such case, demand doesn't change. So it's homogeneous of degree 0. So now summation preserves homogeneity of degree 0. Should be easy to verify in your mind, right? So if you have two homogeneous of degree 0 maps and you combine them with some alpha coefficient, then the summation will be still homogeneous of degree 0, okay? So now, Walras law. So remember that we're assuming monotonicity. So under monotonicity, I know that if I multiply prices times the demand, it will be in the budget line. So it will be equal to price times omega. So that means that if I multiply this excess demand times prices, it will be equal to 0, okay? So Walras law. And then the final 2 properties are basically a consequence of this string monotonicity. And the first thing is that if there is an S constant that is positive, I have that all excess demands are bounded below by minus S, okay? So you can have some excess demand, but it cannot go to infinity, minus infinity, right? So it's bounded by some positive quantity, okay? And then the final part is basically something about prices and what happens when they become free. So say I have a sequence of prices going to P, and then in this vector P is different from 0, but in general, so some prices are positive, but an entry L is equal to 0 exactly, right? So not all 0, but some entry 0, okay? If that happens, then if you take the max over the goods excess demand, some of them will go to infinity, okay? So that means that at least there has to be some goods that are desirable, right? And this is because of the strong monotonicity, that's fine, okay? So as things become cheap, in fact, free, the excess demand goes to infinity, okay? So now, so I have to basically draw this quickly. So let me go quickly to the envision. So, but in between, I want you to basically think about these properties. So these properties are very trivial. They are nothing surprising. And those are the properties that we use in the end to show existence, right? So that's the objective here. They are not particularly interesting in terms of economic intuition. So remember, this chapter is very mathematical. So it's more about trying to find conditions under which we have the existence of our problem, right? But like the intuition really of math, of econ, beyond the homogeneity of degree zero, is not really there, right? And it's fine if you don't find any intuition here because it's more a mathematical chapter, okay? So let me now go to the envision. Okay, so I'm gonna draw this excess demand for a case of two goods, right? So if you have two goods, then remember that by homogeneity of degree zero, I don't have to focus on the two excess demands, right? I can just focus on one excess demand. So this is going to be the excess demand of good one, okay? And this is going to be prices of good one, okay? So then, according to my properties, this is going to be zero, right? And here I'm going to have minus s, which is a constant, right? So now this excess demand will be a function like this, for instance. Okay, so are all the properties here? Yes, because this line, which is an excess demand, is telling me, for instance, in this particular point, that at this price, right, this price 1 star, what is the excess demand here? Is a positive quantity, right? Okay, so where is the equilibrium here, if any? So who can tell me? Where is the equilibrium? So remember that the price has to be such that excess demand is zero, right? So here you have it, right?
Is the x-axis, right?
Yes, exactly. So in this particular model, you have a unique equilibrium, right? So this is the only price at which this excess demand is zero. And the rest of the properties here are also present, right? So this thing is continuous, and this thing is bounded below by a minus s. And as p goes to zero, this thing asymptotes to infinity, okay? So example number 1. And here we have just a solution. Now I'm gonna do a second example. Same problem, we have two goods, good 1, P1. And now I have this object here. So is this sorry, here. I have to erase this part because I went off the line. This cannot become that value, right? Okay. And this is supposed to be going to infinity, right? Okay, so now is this a correct, is this a valid excess demand? Yeah, it has all properties, right? So in particular, it's continuous, right? Is bounded below by the s, and is asymptotic to infinity when prices become zero. But here, how many equilibriums do I have?
In 6, right?
Sorry?
6, right?
Yeah, in this case, right, so we're assuming this is going above forever, just because, but in particular, we're going to show what happens when you have many equilibriums, but here you have multiple equilibriums, right? If this thing goes then away from zero forever, then, you know, then you at least have finite equilibriums, but if it doesn't, right, you can have infinite equilibriums, right? So at this stage, that can still happen. And then let's do yet another one. Set 1, P1, the bound, and then this one is like this. Okay? So you can notice that there is no equilibrium here, right? This thing is always in excess demand. Okay? So there is always a gap here, so no equilibrium possible. Okay, so this system of equation doesn't have a solution. Okay, so you have the three cases illustrated in this. Any question here? Okay, so this is the famous excess demand graph, and you will see it in Masculine. Okay, And remember, in this object is basically capturing the all the information about behavior that you need, because you have aggregate access. So now consider a system. Remember, when I draw this, I said there are two goods, right? However, I only consider one good. So I told I can do this because of homogeneity of the receiver. In fact, claim 11 says this. So consider the reduced system C hat, where you take away the last equation. So you only have L minus 1 equations, okay? And if in this reduced equation, the price makes it equal to 0, right? Then this same price will also solve the original equation, okay? So due to homogeneity of degree 0, you can always delete one equation from this system of equations, okay? And again, importantly, when I talk about uniqueness, I'm talking about uniqueness for the normalized price. So this is only unique up to the relative ratios of prices. So the ratio of prices can be unique, right? I can never have uniqueness of the vector of prices because of homogeneity of degree 0. If there is a price that is an equilibrium, alpha of the price is also an equilibrium. Do you understand? However, it is unique when the ratios are unique, right? Because if only one price vector up to a scale is an equilibrium, then the ratios of prices are unique, okay? So in that sense, it's unique. So when I say uniqueness, I'm always talking about normalized prices, okay? So remember that. So in that sense, and because of homogeneity of degree 0 and Walras law, I can always consider the reduced system L minus 1. Now, do you have to delete always the last good? No, you can delete any good. It's just for simplicity. Do you understand? Okay. Okay, so the big
quick question.
Sure.
How do we know we got homogeneity of degree 0 here? Do we?
So we're assuming here that the
Yes,
consumers are rational.
Okay. Okay.
Yeah.
So that's for an assumption. Okay.
Yeah. So remember, the game here is making assumptions on behavior. So the moment we assume consumers are rational and maximizing preferences, then you have homogeneity as a consequence. Okay. Okay. So just to clarify, so replace our consumer by a sparse max, then you don't have any longer the homogeneity. Okay. So this is because you are assuming everyone is rational, you are maximizing it. Okay. Now, so what is our big theorem for this class? So existence, okay, the elusive existence that eluded Walras and eluded all the economists until Nash, Mackenzie, Arrow-Debreu, okay? So suppose that set P, system of equations size L, is a function, vector function, defined for all strictly positive prices. So remember here, this excess demand is determined for all prices that are in the positive order. And you satisfy the previous conditions that I explained. So from continuity to the asymptotic behavior to infinity, 1 to 5. Then the system of equations basically has a solution. So when I make ZP is equal to 0, here, I don't longer care about the existence of negative excess demand because I have a strict monotonicity, right? So I don't care about that. It has a solution, okay? Hence, our rational equilibrium exists in any pure exchange economy, which has positive aggregate endowments, and every consumer has continuous, strictly convex, and strongly monotone preferences. So, okay, so finally, after almost a century, we were able to prove as econ profession that at least the pure exchange general equilibrium is not trivial. It's even worse than trivial. It's not incoherent, right? So we know it's not incoherent. So at least if you write down this system of equations, there is a solution under these very general assumptions. Now, before moving forward, so a classical question for the core exam is, consider this model, right, where you have these preferences, such and such. And now these preferences don't have one of these properties. For instance, they may fail continuity. So one of the problems that Shum sent you is that you have this you have these floor properties, right? So when you have rounding up or below, which destroys continuity, right? So if you lose continuity, then what happens with the theorem? So the first answer is does not longer hold true. So that means that you are no longer sure that your model has a solution. Now, because this theorem, the nature of this theorem is that these are sufficient conditions, not necessary conditions. It does not mean, and that's the important part to realize for the exam, that there is no solution, right? So a usual wrong answer is the moment you see that either continuity, strict convexity, or strongly monotonicity fail, you will be naively and wrongly believe that existence fails, and that's wrong, right? That's not the correct conclusion from this theorem. It just means that you have to check existence by hand. You can no longer invoke the theorem, okay? It can still exist, right? And therefore, you have to either check by hand that such a solution exists, or show that the system of equations at hand is incoherent, okay? So produces a contradiction, okay? So the moment that any of these conditions fail, you are on your own. So you have to check by hand, okay? However, the other kind of question, which is just, hopefully you get those that are easier, is you have a theorem, even very complex, that satisfy these conditions. So preferences are continuous, the strictly convex, strictly monotone, and of course, you have a pure exchange setup. So then you can conclude existence with invoking this theorem, this proposition, okay? So that's it. So the proof is very long, so it's also very dry, and you don't get much from it. So I'm gonna do a simplified version right now, and then I'm gonna do more a video about fixed points. I'm gonna upload it this week. But here I'm gonna do a simplified exposition of this proof. So what is the plan of the proof? Okay, so the plan of the proof is the following. So we take the original excess demand system of equations, so set P is equal to 0, and we're gonna make it into a fixed point problem, right? So what is a fixed point? Again, is basically a map that maps a price to itself. So let me go to the board. So first of all, this thing you're gonna learn with Maria, and so I'm not gonna dig into this match. I'm gonna do more fixed points for applications to econ later in a video. But right now, what I want you to understand is this simple idea. So a fixed point is a mapping F, right? From some domain to itself, right? So this is a self map. So it's mapping elements in D, right, to some other vector here in D, right? Potentially not the same. So where D prime belong to the capital D, okay? So this is called a self map, okay? Now, what is the fixed point property? So F is said to have the fixed point property, right? Whenever there exists some P star, right, belongs in D, such that F of P star is equal to P star, okay? So now that's a property that some self maps have. Not every self map has a fixed point property. So what are the fixed point theorems, right? So the fixed point theorems, such as the Kakutani or the Brouwers, right? Yeah, the Kakutani is for correspondences. This is the one I'm going to use today. But a simpler cousin, right, is the Brouwer's fixed point theorem. And this basically tells me that I assume that F is continuous, right? Brouwer's. I also assume that D is compact, right? Connected, convex for now, for simplicity. And then under those conditions, I will ensure that there is a fixed point, okay? So if that happens, then F has a fixed point. Okay, so I'm going to do a simple proof of that. Again, this is not in the scope of this class, so I'm not going to do a full proof. This is from math. But the idea is this. So imagine I have this function, I have this box. So this box here, which is nothing to do with the Edgeworth box, it's just the domain D, right? So all this segment here is the D domain. Okay, so this is a compact set, okay? And I'm defining here a continuous mapping, right? So this is the F map, okay? So what is graphically here a fixed point? So a fixed point here, right, is basically the intersection of this continuous map with a 45-degree line, okay? Right? So basically, if this thing intersects, then basically this has a fixed point property. So I think one of the conditions I'm forgetting in the Brouwers was that f of 0 is 0. So I don't remember exactly all the conditions, but you can check them on. You know. But this is a rough intuition of the fixed point. So if you have a continuous mapping, right, with some grounding conditions such as f of 0 is equal to 0, I don't know if that's necessary, by the way, but with continuity and compactness of the set, then you will be guaranteed that this F map has a fixed point. Okay, so this is the mathematical part. And now, what is the econ part? So basically, you want to convert our system of equations, right? Set of p is equal to 0 into a fixed point map. Is this a self map, first of all? Not really, right? Because I told you that set is mapping RL plus, right, to RL. So this is mapping the domain RL plus to RL. So it's not a self map. So the plan of the proof is to convert a set, right, equal to 0 into, this is a system of equations. I have to make a fixed point map that is equivalent mathematically to the system of equations, right? So I'm going to have something else, which is an F thing, that if Fp is equal to P, right, for P star, this is if and only if set of P star is equal to 0. Okay? Do you understand? So this is what Arrow, Debreu, Mackenzie did. So Arrow, Debreu, Mackenzie, they basically rewrote the Wellration equilibrium as a fixed point map. Okay? And the moment they did it, they could apply the Kakutanis theorem or the Brouwers, verifying the conditions in the theorem. Okay? So that's what I'm going to do. Of course, in a simplified version. Okay? So any questions here? Okay, by the way, this is what you will have to do as well if you have your own model. Okay? So in particular, you have a system of equations, and then you can write it as a self map. And then you can apply the fixed point theorems in your framework. Okay? And this will guarantee that your system is coherent. Okay? And believe me, actually, if you're an applied guy, sometimes you have to do it. Okay? Especially structural people. So fixed point theorems are one of the most useful things that you will apply in real life. So this, surprisingly, even if it looks very abstract, this is something that people do, right? And you use, even if you go to work for Amazon, right? Because you have to guarantee the users of your model that your model is not incoherent, right? By the way, so here is an important caveat. So maybe you think this is too theoretical, right? But let's think about the real life application of this. So you are hired by Amazon, you do a system of equations of demand, and you write it down and you present it to your bosses, right? To your supervisors. And then you didn't solve the fixed point problem. You didn't verify it. You don't know if a solution exists. You just run it in Julia, right? And then you came up with some numbers, right? But when solving this system, you never check. Basically, your objective, right, which is basically a quadratic form of this set. So how will you solve this in Julia, by the way? So there are two ways, right? So the first thing is basically trying to write down first order conditions and then solve a system of equations, right? Which there is some packages to do it. And another is basically to rewrote the objective, set P as a quadratic objective, right? Like in GMM, like with naive. So set P is a vector, right? So you multiply it by set P. So the transpose of that, it gives you the norm of set P, right? And then you minimize this with respect to P. Minimizing this norm when exactly 0 by the properties of the norm means that if the norm of this set P equal to 0, along is 0, that means that set of P is 0, right? So that means that something that achieves the zero in the objective will be a solution to your problem. Okay, got it? So now the important thing here is imagine numerically you're very close to zero, but you are not zero, right? Are you sure it's a theoretical zero or it's just some numerical noise? You cannot be sure, right? It can be like the example that I gave you where you're always in excess demand, just a bit off, right? So it turns out that your model has no equilibrium, right? So these are actually important things. So a numerical solution to this problem won't give you a true solution, a true guarantee that your problem has a solution. It's not incoherent, right? So applying the fixed point theorems, you actually will be able to conclude this. Okay. So with all that in hand, justifying this, I'm going to give you the fast version of this. And so the first step, as I mentioned, is that we cannot guarantee existence because of these issues with homogeneity of degree zero. So the first step I want to do is normalize prices. So how do I normalize prices? Well, I'm going to define the set of normalized prices that are all prices such that the summation of the prices is equal to 1. So what does it mean? So it means, give me a price, for instance, 1, 2, right? If I sum 1 plus 2, it gives me 3. So this price is not in this set. How do I transform it to put it inside this set? So I take the price 1, 2, right? And I divide each entry by the norm of this price, right? For instance, right? Or basically I can also divide it by the sum of the prices, okay? The sum of the prices is simpler. So what is the sum of the prices? 3. So I divide the first entry by 3, so it's 1/3. And the second entry, 1, 2, sorry, 1, 2, 1, 3, and the second entry is 2, 3, right? And then of course the summation of 1, 3 plus 2, 3 is 1, okay? So you can normalize these vectors by the sum of them. So if you take the relative prices of this new vector, it's the same, right? It's still the relative price of 1/2 is 1/2, right? Irrespective of whether are normalized or not. Do you understand? So the relative prices are not going to change with this normalization. So full-fledged name that you have to remember, we're dealing only with normalized prices, okay? So these are prices that behave like probabilities. They are non-negative and they add up to 1. So hence, I'm using the simplex notation, okay? Do you remember this triangle notation, the simplex notation? We use them in the expected utility chapter to denote elements of the probability distributions, right? So here prices numerically, they behave like probabilities, okay? Because they are positive, non-negative, sorry, and they add up to 1. Got it? So now prices, if I say prices, I'm talking about elements in the simplex, okay? Now, so because the function is homogeneous of degree 0, we can restrict ourselves to prices here because only relative prices matter. Now, first of all, I want to notice that because of the strict monotonicity, my excess demand is well defined for elements inside the simplex. So a simplex has an interior, which are entries that are always strictly positive. For us, it means strictly positive prices. Do you understand? So when I say boundary of the simplex, I mean prices that have 0 entries, okay? Because they have to add up to 1, you can never have all entries equal to 0. Do you understand? But some entries can have 0 entries, okay? Some, not all, because they have to add up to 1. Got it? So they behave like probabilities. So if you have, for instance, 3 prices, if 2 of them are 0, the third one has to be equal to 1, okay? Understood? So now, if we exclude these cases, the 0 prices, we are in the interior, okay? And I'm gonna call the interior simplex by the super I on the triangle, okay? So, and then, you know, basically the excess demand for any positive price is well defined because this is actually a function that is, because of strict monotonicity, will produce a non-infinite number for prices that are non-zero, okay? You know, as prices goes to 0, the demand goes to infinity and it stops being well defined. Got it? So prices in the boundary will blow up the excess demand. So when I say well-defined, I mean they haven't blown up. Okay, got it? Now, okay, so here comes the heavy artillery of Arrow of the Brew. Okay, so Arrow of the Brew, you know, they sold it as the main contribution better than Mackenzie because they didn't use the Brouwer's fixed point theorem, which is for functions. They applied the Kakutanis, which was fancier, that applies to correspondences, right? What is a fixed point for correspondences? So instead of mapping the domain of the simplex of prices here to the same simplex of prices, it maps the simplex of prices to the power set of the simplex of prices. More very like the correspondence, right? So if I evaluate in this F correspondence a price, it will give me a set of prices. Okay, so this is like a choice correspondence. If I give it a price, it gives me a set of prices. Okay, do you understand?
Sorry, I'm a little bit confused here. So,
Sure.
so the triangle
Yeah.
is the set of prices that would add up to 1.
Yep.
And when you input those prices to this function,
Gives you a set.
a set.
Yeah. So let's draw it, right?
Okay. Yeah.
So say I fix the price, P equal to, this is 3-dimensional, right? So let's fix it to 1/3, right? Okay. So if you have this now, and what is going to be the F image of this, right? So potentially it can be this area here. Okay. So in other words, if I take F of the price P here defined 1/3, 1/3, 1/3, it gives me this area. Okay. So this is mapping a price vector to an area in the simplex. Okay.
Sorry, what does the area represent again?
It's a collection of prices. For instance,
Collection of
this
prices.
can contain the same price, for instance, right?
Mhm.
But other stuff, like for instance, here there is some entry that has 0, right?
Oh, okay. Oh, okay, okay.
So again, so an important tip for understanding this chapter is forget about the econ for a second. It's just math games, right? So right now we're just doing the setup. This is a correspondence that takes as inputs a price and gives you an area of prices inside the simplex. Do you understand? Nothing else. Okay. So this is just the setup. So no econ intuition right now. It's just a device that I will use for using the fixed point argument of Kakutani. Okay. So what is now a fixed point in the world of correspondences? Okay. So well, easy enough. A fixed point in the world of correspondences means that the P star, that is the one I'm evaluating the function f, the correspondence f at, belongs to the area. Okay. So namely, if I take P star as an argument, the P star will belong to the area in the image of f. Do you understand? So let's go back to the graph. So as I mentioned, what we're doing now is just a generalization of the idea of fixed point that I hope you already understood for correspondences, right? So basically you have two triangles here, right? It's the same triangle. So right now, say that I take this point in the middle, right? And now this maps to this area here, right? Through F. So is P a fixed point of this map? Yes. Tyson says yes, he's correct. P is here as well, right? That's what I'm saying. Okay. So this is mapping these two areas in the triangle. If the area in the triangle contains the original point, it's a fixed point. Got it? That's a correspondence fixed point. Okay. So nothing too fancy, is still understandable, right? So now we go back to the Arrows-Debreu proof. Okay, so now what is the trick? So the whole trick of this proof is to create, and I highlight, create an f such that it has a fixed point property. And when that fixed point property happens for some P star, that P star is a solution to the original system of equations, aka our excess demand general equilibrium system, okay? So this is what I have now, an excess demand model, right? That comes from preferences, utility maximization. So I write down the system of equations, and now Arrow de Brue writes an parallel f, right? Which is a new mathematical object with this property. We haven't built it yet. So right now we're just claiming we're gonna build it, okay? So this is the plan of the proof. We haven't done it, okay? Once we do it, then we will verify properties on f such that they come from the properties of set, obviously, because these two are connected. And once we have proven that the conditions under the Kakutanis theorem hold, we will conclude that f has a fixed point, okay? Right now, the only thing we want is a map such that if it has the fixed point property, the fixed point will be a Wallratian equilibrium, okay? Got it? So now, as a corollary of this, if you show existence of a fixed point, we know immediately that the Wallratian equilibrium exists. Do you understand? That's it, okay? So the rest is the heavy part. So I'm just gonna show the part that is not crazy, right? Which is the first part. And is for the interior points or prices in the interior, I'm gonna define f of p as all the prices q in the simplex such that the multiplication of the excess demand evaluated at p, the argument, multiplied by q is in the image, right? Is in the area, is greater than equal than set of p multiplied by q prime for all q prime in the simplex. So this has a flavor of revealed preferences, right? So let's understand what it's saying. And that's the main thing we're gonna learn from this fixed point part, because the only one that actually matters. So what I'm doing is this. So I have the excess demand evaluated at prices, right? So this is how much excess demand I have when prices are P. So if I multiply it by Q, right? This is telling me basically a counterfactual quantity of how much will I spend in terms of demand and how much will I have in terms of excess money at prices Q. So if my demand was a set of P minus omega, right? If I multiply it by Q, so let's expand this so you can see it. So remember that set of P is the aggregate demand, right? Minus the omega. Okay, so if I multiply it by Q, so remember this is an inner product, so commutativity works here, right? I have that this is the multiplication of the demand times Q, right? Just for simplicity, let's write this here so you don't get confused. So this is, of course, I'm assuming representative agents here for simplicity. So what do you have here? You have a multiplication. So this will give you what is the expense I will incur when prices are Q and when this is the desired demand and the price is P. And this will give me the money that I will have under this price Q, right? And when this excess demand, counterfactual excess demand, is greater than equal than any other counterfactual demand when prices are Q prime in the whole simplex, then, you know, this will essentially be a point in the image, okay? So now let's see what happens when if this price is an equilibrium price. So if P is, so if Q is equal to P star, so let basically be P is equal to P star, right? And Q be equal to Q star as well. Then what happens? So then I know that set of P star, right, is equal to 0. And therefore, if this is 0, 0 vector, any positive price multiplied by 0 is 0, right? And then the interesting thing is that for the second part is also, so basically you have this inequality, which holds always, right? So for any P star, this inequality is satisfied trivially, right? So that's what happens here because the set of P is 0, okay? So that's basically the construction. So now let's think of a price that is not in equilibrium, right? So you have always a negative quantity, right? So now you have a negative quantity here and you multiply it by positive prices, you have a negative quantity here as well, right? So now basically you can change your Q star for any other Q such that it blows up a different quantity, and therefore you can have the first entry being negative but above the second. So any price that is not in equilibrium will not be there, right? So this is basically trying to capture the equilibrium part. So this part is just intuition, but the construction that the Brio did is basically this construction here. So you put in area of prices, all the prices that satisfy this inequality, okay? So that's the first part. And the final part is basically trying to do trying to take care of the boundary conditions. So now what happens if you have some prices that are 0? Then you have to make sure that the image doesn't blow up, right? And the image are always prices. So in particular, whenever you have an entry price that is equal to 0, right? And then for the price, you are not blowing out to infinity, then you speed out the whole area, right? And the step 2 is basically the long part where I'm going to skip, which is basically giving you different areas for the points in the boundary. So remember, the points in the boundary are not important economically because of a strict monotonicity. Any equilibrium is a positive price, right? So why did Arrow of the Brio include them and spend so much time correcting this to include the boundary of the prices? Because Kakutani's theorem needs the domain of prices to be compact, right? So if I erase the boundary of the simplex of prices, I have an open set, right? So Kakutani's theorem does not apply, right? So that's the very work that a theorist has to do, right? So the theorem of Kakutanis applies for compact domains, right? So if I consider the economically meaningful set of prices, which is the interior of the simplex, the theorem of Kakutanis does not apply, right? So I don't want to reinvent this. I'm sure there is a way to prove some version of Kakutanis with open sets that are convex, but that's not Arrow's de Brio work. They instead create this F to include the boundary, basically doing tricks, right? Such that you are able to map F to, which is a compact set, to the power set of the simplex, which is also compact set, okay? So it's about compactness. So this is not econ, is math, okay? So the adding the boundary points, which are prices that are never equilibrium, okay, are important because the Kakutanis theorem requires the domain of this map F to be compact, okay? Do you understand? So what Arrow de Brio are doing are compactifying the domain of prices, okay? So step 3 is the same. This is the long part that I'm going to skip. And basically, once you have done it, right, you want to check the following properties to apply the Kakutanis theorem. So the Kakutanis fixed point theorem, given that we have correspondences instead of functions, obviously requires some form of continuity, right? So because these are correspondences, continuity is no longer a goal. So you need something weaker than continuity. And what I need is basically to show upper continuity, right? We already know this from chapter 3. And upper continuity turns out to be insufficient, right? We also need it to be convex valued, okay? So what I'm asking this F that I constructed is basically that if the area of prices, you take any two prices inside this area, if the convex combination of them is still in the image, right? So convex value, the areas of prices are always convex sets. and is upper ME continuous. We already learned this from chapter 3. Okay, so the step 4, which is the heavy part that I'm going to skip in this class, basically involves checking that the construction I just did is upper ME continuous and is convex valued. Now, remember that the economic part, that is the important part, is that for non-boundary points, this function, this correspondence, sorry, is defined in terms of this system of linear equations that depend on the continuous function set, right? So this will give me continuity of the correspondence in interior points. And the inequalities, because they are linear, they are going to give me convexity on the interior points. So the complexity of the proof really resides in checking the boundary cases, right? And the boundary cases is a very long proof that you have to check that all of this holds, and basically it's just their work. So, and you use here the properties from 1 and 5 that I just described in the previous proposition, combining the values of set with these different properties, such that I'm able to show that the fixed point correspondence that I created is upper ME continuous and is convex valued. So now I have 3 things. The domain of this fixed point correspondence is compact, is the simplex of prices, is convex as well. Second, the fixed point correspondence is upper ME continuous and convex valued. So if I have the 3 things, I can apply Kakutani's fixed point theorem. Okay. So Kakutani's fixed point theorem, right, says that a convex value upper ME continuous correspondence from a non-empty, importantly, compact, and convex. Convex, we don't care. That's easy, right? Compactness is, we did all the work because of compactness, right? Set to itself has a fixed point, right? Since the simplex of prices is compact, not empty, and convex, and since the f I created by the previous steps that you can check, I'm going to do a video about, is convex value, upper ME continuous correspondence from the area, from the simplex of prices to an area of the simplex of prices, we conclude that there is a fixed point such that P star belongs to f of P star. And of course, the key is that Arrow-Debreu constructed this f such that any fixed point here in the F map is a solution to the system of equations, okay? And this is a Nobel Prize winning proof, right? So important teachings. So why it takes so long? Well, before Nash, around the 60s, there was no fixed point terms, right? So these were very recent innovations by mathematicians, right? So Nash was a mathematician already, so he knew about these advancements, and his genius was to, at least for the econ part, was to recognize that you can write down these. He also did modeling, by the way, but he recognized he can write down these models of strategic interaction in the fixed point setup, and then basically you can prove existence and make this model coherent. Okay, and once people realize you can do that, right? He was the first guy. Then everyone said, wow, so that's what you have to do, right? So everyone knew in the 60s that the way to prove general equilibrium existence, the open questions and the Walras blunder, was by using fixed point terms, right? And of course, then Mackenzie did it with the Brouwer's fixed point theorem, which I think is enough of a good proof. And Arrow-Debreu did it for the general case, right? Which is slightly general. And so what they did is basically they are not inventing the math. They are just being creative to be able to put our setup, the general equilibrium setup, into a fixed point setup that Kakutani knew how to solve. Okay, so for your future research, that's what economists do, economic theories. So you have to keep up updated in terms of math, new developments of math, right? Then you recognize an econ problem of interest that has been unsolved, right? And then basically you have to rewrite the economic problem at hand, that is usually very, is the non-trivial part, the econ theories work, into the setup of the mathematicians, such that you can apply the results in math, right? And that's exactly basically the bread and butter of econ theories. So that's basically what a lot of us do. Not all of us, because a lot of econ theory is mostly modeling, right? Which is different from this, which is more creativity. But you know, the heavy theories, like Arrow de Breu, you know, the heavyweights, they did this. Basically, they're applied mathematicians. So they don't invent new math, they applied math to hard econ problems. And they just realized how to rewrite the hard econ problems into the math setup so they can apply the theorems, okay? And now, what does an applied guy do? As yourselves, potentially, and very likely. So instead of showing the fixed point theorem every time, maybe you have to do it in some cases. In many instances, you just have to invoke the results by Arrow and de Breu, right? So Arrow and de Breu will prove it to a level of generality that you can use it in most applications, right? So at least in this class, I'm giving you the version for pure exchange. But if you become a macro guy, you will learn extensions by Schonenstein, Arrow de Breu, Scarf, and others that generalize the existent theorem for economies with production, with infinite time horizon, with continuous of goods, with continuous of agents. So this was all the rage in the 60s, right? So it was so much that there is very few open questions in general equilibrium. So they exhausted it, right? So they prove all theorems, of course, with full attention, right? So you can see where you can do new stuff. But yeah, so general equilibrium as a branch of econ theory is basically today almost dead, right? Because all these guys were so excited about these results and this new math that they prove it all, okay? And they got many Nobel Prizes and good jobs. But now it's done, right? Unless you add some new thing, right? Attention, right? Which obviously what we're doing. So I wanted to tell you this because I want you to understand how research works, right? So this research for applied guys, for theory guys, is about keeping up with the math results, right? So new innovations in math will help you solve open questions in econ, okay? And then for the applied guys, it's also useful to be updated in the most general theory, because then you can actually show that your models are consistent and you can be sure that you're doing something sane, okay? Again, so if you're working for Amazon, remember that stakes are high, right? So Amazon, for instance, pays in terms of actual performance, right? So if your model is bad, you're gonna get paid nothing, right? Potentially fired. So econ is becoming a real practice. So you are becoming more like engineers. So now you have to be actually even more serious than before, right? Because if your model is bad, you know, it's like engineer, right? So your bridge is gonna collapse. So your pricing model for Amazon is gonna be bad, and Amazon is gonna lose money, and you're gonna get kicked out. You see? So when you become like engineer, things get serious, right? It's no longer, you know, yeah, blah blah, fixed point, right? It actually becomes very relevant. So the fixed point is important because now you know for sure my model is not incoherent, right? So I'm catching the bug in the modeling, right? So that's why you need it. Okay, so remember this, I'm highlighting this because I'm sure this is a very big punch for most of you. It's very heavy, but when you are modeling, you can come back to this chapter and to these ideas, right? So this is very, very useful. So this is one of the most useful ideas, the fixed point idea, right? And I will tell you, if you do econ modeling, system of equations is the bread and butter, right? So this is what people do for a living, okay? Okay, so again, the proof this time, I'm not going to go through the details because mainly is this dirty work of trying to define this fixed point mapping. And really, you know, what you're learning is, you know, the hard work of years that Mackenzie, Arrow, de Breu did to be able to fit this into the Kakutanes theorem. So you're not going to learn anything really, right? Because this is the spark from Arrow's de Breu. So I'm not sure by repeating proofs you can learn your own spark. I think you develop your own spark in proofs, so your own innovation capacity by creating new proofs. By repeating proofs, you won't learn anything for sure in terms of a spark. You can apply this term and you know how it works as a system, right? I told you how it works. But repeating these nasty details and the dirty work won't give you a spark, okay? But remember that there is a lot of innovation and creativity in trying to write down this fixed point problem, so the original general equilibrium as a fixed point problem, okay? And so this is basically my main message here. Okay, so any question here? Okay, so crown jewel on the econ theory hat, right? So existence. Finally, Leon Walras, can rest in peace. We know there exists an equilibrium, so therefore he wasn't really completely wrong, right? He was right for wrong reasons, right? Which sometimes, as an engineer, that can happen, right? But that's fine. And then, so now the next question. Okay, so great, we show existence. And then what is the next thing you want from a model? So you want uniqueness, right? Because if you're making a prediction about behavior, you would like to be exact on predictions, right? Or what is your take? Do you think econ model, a system of equations, has to have a unique prediction, so for a unique price at which everything clears, or are you fine with multiple equilibria? So, and what is multiple equilibrium in the world of general equilibrium? So in the world of general equilibrium, it means that in the Edgeworth box, for instance, you can have two different prices at which markets clear, right? For the same endowment. So what do you think about that? Do you think uniqueness is desirable in some way? What's your take? This is a modeling question, by the way. We have a few minutes, so we can just talk now philosophy, because we're not going to go through the existence there. But yeah, so what's your take? So do you think it's even desirable from the point of view of just being a predictive science to have multiple equilibria? Or do
What
you
does
think,
like the data show, like in the real world?
well, but that's very hard to do, right? Because multiple equilibria is very hard to observe, right? So think about it. So think of the simple case of an experiment, right? So you put two subjects in a room, right? We call it the Edgeworth box. We give them endowments, so 10 apples and oranges, split half, and then I let them exchange, okay? So if I observe a trial, I observe just one potential trial of the true function, right? So can I observe really multiple equilibria? So to observe multiple equilibria is kind of tricky, because like potentially we have to have a parallel world, right? Where these guys, the same guys, exactly copies of everything, end up with a different choice. So can you do that in real life? So first, if I run this in the experiment by giving them the same endowment in repeated times, it's very hard to control for all things that are changing. For instance, you can get fatigue, you can get tired, right? You can get, you like the other people, the other guy's face, you think it's a trustworthy face, right? This is a common bias. Some faces are trustworthy. So I say, I can make businesses with this guy, right? And then, you're going to exchange more, better terms, right? How can you control that? So observing multiple equilibria amounts to have a parallel world where everything is the same. And then in one world, you have the exchange rate 1 to 2 apples, right? 1 orange, 2 apples. And in the other, you have 2 to 1, right? So of course, we can write models with multiple equilibria. But in real life, can we actually have multiple equilibria? Well, let me tell you this. So some people in macro development claim that sometimes you can find parallel worlds in the wild, right? Well, applied guys know all about the spatial regression discontinuity, right? But I'm going to tell you a simpler example, right? So imagine, for instance, North Korea and South Korea, right? Very sad situation, right? Historically tragic. But so from the point of view of econ, right? What happens there? So you have pretty much a country that is very population is very homogeneous in many dimensions, right? I know there must be differences, but from the broader perspective, they are very similar in the whole Korean country, or the original country. And then, for external reasons, right? So powers playing there, it gets cut in half, right? And the North Korea becomes, so a socialist experiment. The South Korea becomes a capitalism experiment. And then, you let this experiment run for several years. And then you got yourself an outcome, right? So is this a way to observe, you know, multiple equilibria? So in this case, there is a selector of them, and that's another question, important question. So with this I'm done. So in the world of multiple equilibrium, general equilibrium does not tell you which equilibrium should happen, right? It tells you any of these things can happen, right? So you are leaving out of the scientific prediction the selector of the equilibrium, right? So in the case of North Korea, is you know, an economic system, right? But you know, the selector can be anything, right? For instance, in the story of the parallel worlds Edgeworth boxes, it might be that in parallel world number 1, a fly was going around one of the traders, right? And he got distracted. You know, these are things that you know that are very important, right? And they get very, very esoteric. So macro people like something like sunspots. It's an actual serious branch of macro, which I actually like a lot, by the way. It's just funny in the name. So they try to find ways that these multiple equilibriums get selected by some sort of self-fulfilled equilibrium, right? So everyone kind of wishes to be in some equilibrium, and they together they come to it, right? So they coordinate on sunspots, okay? So, and also, by the way, check on Wikipedia the effects on sunspots on, you know, on econ and societies, right? It's very interesting. So, in short, right? So, multiple equilibria sounds cool, and sometimes is part of the mathematical model, but in terms of empirics, it's a nightmare, right? So my main message to you is we want uniqueness, right? And for applied guys, except game theories, but for most people that are doing non-strategic setups, the norm is to have uniqueness, right? So basically what we're going to do is try to find sufficient conditions such under which we have uniqueness, okay? Because this makes our predictions more sensical, right? Now, again, I'm not discarding multiple equilibrium. There are branches of macro that depend on that. Game theory depends on that. I don't think game theory is doing very well because of that, but it depends on that. It's a reality, right? That's actually an issue with general equilibrium, sorry, with game theory. Uniqueness is something that theory should have, right? So yeah, but multiple solutions of these systems can happen mathematically, right? But that doesn't mean that reality, you can even observe this, right? You have to observe multiple parallel worlds, which is a headache, right? But again, we also use this kind of non-deterministic approach with the choice correspondences, right? So in the end, it doesn't forbid mathematicians from writing down correspondences, right? We cannot stop them. But we have to be aware that these are potentially problematic from the empirical point of view, okay? So that's it. So I'm going to take questions and you're free to go otherwise. I'm going to stop recording as well.